Hello everyone. Today we are going to start in a new material, which is diode circuits rectifiers. Okay, so we will have some diode circuits in this class. The first circuit we will discuss in the diode applications is rectifier. So what the meaning of rectifier and the applications. We will discuss all of that together. So the objectives of this material, we may need some classes to cover this material, not only this class. So it's up to our progress. So in this part of the course, the diode rectifier circuits, you need to know how to determine the operation and characteristics of a diode and rectifier circuit, and analyze the performance of diode rectifiers, analyze the performance of rectifier circuits in DC power supplies as one of the important applications for the rectifiers, and inspecting the diode rectifiers on PSpice simulator. So let's start firstly, guys, with the concept of a rectifier circuit. So, guys, all that the nature of our conventional grid is AC. So the regular supply we have at homes is AC supply. So all the available home supplies are AC. So this is the main supply we have. But we have a lot of DC loads actually in our life. For instance, if you see the loads at home, you will find, for instance, that all electronic devices are DC. So all electronic devices needs DC supply. Some types of electrical drives use DC motors. So, or even some types of the AC motors needs to be controlled by means of what's called the back-to-back converters. So it includes actually rectifier and inverter. So it's well known as inverter-based devices, like in air conditioners, for instance. So air conditions also needs a rectifier circuit. So just a moment, guys. So in this case, guys, we find that rectifier is very important because you have a lot of applications needs DC or controlled AC, and all of them require the existence of a rectifier in our circuit. So we need to understand now the concept of rectifier. So the rectifier firstly takes the original AC supply from home. So since the main supply is AC, so this supply is AC coming from the company, electrical company, and supply it to any home. So first stage, the volt we have in the AC, the regular domestic load, is 110 volt, 115 volt. So this is the range of the AC input. Let's say, for instance, 110 volt AC. But all electronic components, we use it in small devices, like in electronic devices, like television, like any electronic circuit you have at home. The volt is relatively small. For instance, it needs 5 volt, it needs 12 volt at most. So in this case, guys, we need a first step to reduce this voltage level. How can we reduce the AC volt? By using what's called power transformer. So the power transformer is going to step down the volt, for instance, from 110, let's say, to 12 volt AC, or different levels. It could be 6 volt, it could be 5 volt, whatever. And then next step, we need to convert the AC supply to DC supply. So the output of the transformer is still AC. The output of a transformer is AC, because transformer actually is electromagnetic AC device. Okay, we don't have what's called transformer in DC. Only transformer is AC machine. So the output is still AC. AC, the ideal AC, guys, we have is sinusoidal supply. But the difference between the input and output is the voltage level. And we will see together the relation of the primary to secondary volt of a transformer and what's controlling the transformer volt inside this device. Then in the rectifier circuit, we will find the next step, which is used to convert this AC to DC. But it's not going to be pure DC. So what we will have here, we have something called half controlled, we have something called full controlled, we have something called half wave, we have something called full wave. So for the diode, we don't have control, it's only uncontrolled. So for the diode circuit, you will have uncontrolled half wave and full wave. And we will see together the difference between everyone. So the half wave is going to be like that. This is the output, and the full wave is like that. So this is full wave and this is half wave. Can you see, guys? This is still not pure DC. This waveform still has ripples. Ripples mean the value is going up and down. So it's not pure DC. So in order to have a pure DC means you need a constant value like that. So this is called pure DC. In order to have a pure DC, you need to input this waveform to a filter in order to have this output a pure DC here. What is the filter inside? We will discuss about this later on. After that, after filtering, the voltage magnitude here, we need this volt to be regulated. What's the meaning of regulated volt, guys? Actually, regulated volt means, so the word regulated volt means actually three important things here, which are controlled volt, continuous volt, and constant value. So we need a regulated supply. Regulated supply means when you make a load here on this supply, this volt should be constant enough. Any kind of loads, guys, if you apply a load to an unstable supply, the supply volt should be reduced. It's like someone has power, but you give or you made high load on him. So in this case, his power will be reduced. So it's similarly here in volt. So if you have unregulated volt of, for instance, 10 volt, and you suddenly absorb certain amount of current, so this volt will be reduced, for instance, to 5 volt, to 7 volt, whatever. So this is called unregulated volt. But for a rectifier circuit or for a DC power supply, you need to have a regulated supply. Okay, so this is, guys, the concept of a power supply. So we need all of these parts in a power supply, starting from transformer, rectifier, it could be diode rectifier, it could be transistor-based rectifier. We need filter, we need a voltage regulator. So these are the main important steps we needed in a power supply. As you can see, guys, the diode rectifier is one essential component of our power supply. Let's start one by one from the transformer. Some of you guys may already learn what's called transformer in electrical circuit or electrical machines. Just a quick revision. So transformer is electromagnetic device. It has input supply, AC. The output supply is AC as well. And the voltage can be controlled by means of the turns ratio. So the relation between the primary and the secondary volt is V1 divided Vs or Vi divided Vs equals N1 divided N2. Or let's say, if you would like to say 1 and 2, you can say also V1 and V2. So we can say V1 and V2, where V1 equals Vn and V2 equals Vs. So this is the relation between the input and the output. Now, the concept is relatively easy, guys. So what we need, if you need a step-down transformer, which means V2 should be less than V1. So in this case, N2 has to be less than N1. So we can make a certain winding transformer with a certain turns ratio. Turns ratio means the ratio between N1 and N2 in order to achieve the required volt. For sure, you don't need to make winding yourself. These transformers are already designed and it's ready in the market. So on-shelf solution is available, so you can get it easily. So this is the first step, guys. Let's read together the important note here. So the input volt or the input signal V1 is the general AC volt, which is 120 for instance, 120 RMS volt, 60 hertz. So this is the supply volt we have. By the way, guys, I said in the previous slide it could be 110 or 115. Now we said 120. So what's the value? Should be 120, 110, 115. Okay, actually, guys, this depends on where is your place from the main transformer. So all of these voltages, guys, 110 is correct, 120 is correct, 115 is correct, but the voltage or the system itself, it could be, we can say it's 110. But if you have a transformer very close to a house and you don't have a lot of loads on the circuit, so this means the voltage drop across the cables in the street will be less. So in this case, you expect a volt in the first house close to the transformer to be relatively high. So actually, the domestic load 120, 110, 115, it could be any of these, depends on how far is your house from the transformer. So if the transformer is relatively far from your house, so the volt would be less. If the transformer is very close to your house, so the volt would be high. Okay? But by the end, we call it single phase domestic load or domestic supply. Okay. So this is the input. We have ideal. We have 120 volts. Okay, and here we have the ratio of the ideal transformer. For sure, guys, if you already learned electrical machines before, you will know what the meaning of ideal transformer and practical transformer. If you didn't learn these topics yet, these topics will be learned in electrical circuits too and in electrical machines classes, so this will be very clear to you. But for the time being, let's assume that we have an ideal transformer. Ideal in our life, we mentioned before, guys, ideal is something like impossible. We don't have it in our life, but we use it just for simplicity. So the practical transformer compared to the ideal transformer, you cannot apply this voltage ratio. You will have some losses inside this transformer and some voltage drop also across this transformer. But let's see, because this is not our topic now in the analog electronics class. So let's assume that we are going to work only with ideal transformers. So for the ideal transformer, guys, we will apply the relation N1 divided N2 equals V1 divided V2, where N1 and N2 are the number of primary and the secondary turns ratio. Primary means the primary winding here, the first winding, and secondary means the secondary winding here. So N1 to N2 is the number of turns of the primary and number of turns of the secondary side. The ratio between N1 and N2, so N1 divide N2 is called turns ratio. Turns ratio. So the transformer turns ratio equals N1 divide N2. The transformer turns ratio will be designed to provide a particular secondary voltage Vs or V2, which in turn will produce a particular output voltage Vout. So here, the output of the transformer itself, it's V2, and for sure you will have some voltage drops in the middle. You will convert the AC to DC by means of this diode, and by the end we will have Vout on our connected load here. Okay. If you would like to draw the relation between V out and Vs, you will find that the relation is linear, but there is an intersection here with the horizontal x, Vs, which is V gamma. What is V gamma? Right? You are right. So V gamma, we discussed this before. V gamma is the turn on voltage of our diode. Why? Because as you can see, if this is Vs, the secondary volt, the AC secondary volt, and this is V out. If you apply Kirchhoff voltage law, you will find that Vs equals V out plus volt across our diode here, which is Vd, and this is gonna be nothing but V gamma during turn on. So this is the relation or the expected characteristic of the output of our rectifier. Okay, guys, so this is the shape. As you can see, guys, if volt is less than V gamma, we have zero output. So this is not working if Vs is less than V gamma. Why? Because if Vs is less than V gamma, this means this diode will be turned off. It's not connecting anything. So the output voltage, the current is going to be zero, and the out for sure, zero times the resistance R, it will be also zero. So this is now, guys, the characteristic of this circuit, or we call it the output characteristic of this circuit. Let's see the operation of our rectifier. We said before, guys, V gamma is the turn on volt. We can get these values from the data sheet. And we said before it's going to be like 0.4 to 0.7, 0.8, this range depend on the semiconductor material which is going to be used. Assume that we have V gamma equals 0.7 volt, for instance. So what will be the shape of the output volt if the supply is AC like that? So if this is the AC source, let's say also because we have here the 0.7 is relatively clear in the diagram. So let's say the peak value of the volt here, I'm going to assume this is a small value of volt. Let's say, for instance, 3.3 volt. You know, 3.3 is one of the levels we need it a lot now today in our electronic circuits. So assume this is 3.3 volt. So what will happen in order to operate this rectifier if the supply is 3.3 volt? 3.3 is the peak value, by the way. Okay, so this is the peak value, 3.3. So the RMS value, if I would like to get Vs root mean square, so it should be V peak divide root 2. So this should be 3.3 divide root 2. And root 2 is 1.4 something. Okay, so this is the concept. But let's assume now we have a peak value of 3.3 volt here. Okay, so what will happen is this diode, so the circuit again, we already could see the circuit in the previous slide, but let me draw the circuit here, somewhere in this slide here. So if this is our circuit, so this is the output of the transformer, we have diode, and then we have our load here. So this is the secondary of transformer, and this is the diode here. And this is here V out, and this is our resistance. So this diode will be turned on only if the supply volt is greater than the barrier volt of our BN junction, which means it should be greater than V gamma. So as you can see here, guys, if this is V gamma, during the period from 0 time to this instant, the diode will not be on. The diode is off. And if the diode is off, this means V out should be off, should be 0. Okay, so during this period, you don't have any output. And once you turn, so as you can see here, guys, the first period here, V out equals 0. And once you have Vs, the dot line here, Vs greater than V gamma, so this means the diode will be turned on. Turned on means now the output volt will be Vs minus V gamma. So this is going to be now the shape of our output volt. Until which time it will be continue turned on. We mentioned in the last class, guys, the diode turn off condition is when the diode current reach to 0. So the condition to turn off a diode is I diode equals 0. So since this is a resistive load, and you know, guys, for any resistive load, the voltage and current are in phase all of the time. So if we have a resistive load, this is a phasor diagram. If this is V, so I should be in phase. So this means this is for R load. So this means, guys, the voltage and the current should start and end at the same point. So this means the current will be 0 at this point also. So once the current turns off to 0 here, once the current reaches 0 here, this diode will be turned off. And once the diode is turned off, the current will be 0, and as you can see, the out became 0 again. Until which time? Until Vs return back again to be greater than V gamma to that point. So in this case, guys, the output volt here we have V out peak value is nothing but Vs peak value minus V gamma. According to our assumption here, if this is 3.3, so the peak value will be 3.3 minus 0.7. Okay. So we can say here from this relation, I diode equals Vs minus V gamma divide R, and V out equals I diode times R, which is Vs minus V gamma. And these are the relations of our simple circuits. One important thing, guys, is the voltage drop across diodes. So this is actually the voltage drop across diode. How can we get the voltage drop across diode? Again, this is our circuit, so this is Vd. We can say Vd equals Vs minus V out. So here you have Vs in this red color in the first wave. The black one here is V out. So just subtract the two waveforms. So you will end up with this relation. So here we have V gamma. The peak value here is V gamma. And during turn off, V diode equals the same value of supply volt. So this means the peak volt we have here is the same V peak of our supply. For instance, this is according to our example, 3.3 volts. And during turn on, during this period, during turn on, yes, the volt across the diode itself is going to be V gamma. Now, guys, I give you an example of 3.3. Can you imagine if you have a supply volt of 120 volts and the turn on volt or V gamma equals 0.7? So in this case, the peak value of the output volt here would be 120 minus 0.7. So 121.3 volts. This is going to be the peak value. And here for the negative side, it would be minus 120 volts. This peak is going to be minus 20 volts. And regarding the volt during turn on, it's going to be 0.7 as it is. Why I'm giving you this example? Because if you are working in a power circuit, we neglect the 0.7 or turn on volt to the peak value of the AC volt. Okay, but for small voltage values, as you can see here, 3.3 volt compared to 0.7, no, this is a big value compared to the 3.3 volt. Okay, so this is, guys, the waveform of our circuit. By the way, guys, this circuit is called half wave rectifier. So this is called half wave rectifier. Okay. Let's solve this example together. So in this example here, the objective is to determine the current and voltage in half-wave rectifier circuit. By the way, let me bring the previous slide again, guys. I have a question here. I need this point to be crystal clear for all of you. The first waveform here, this volt, is it AC or DC? And the second volt here, is it AC or DC? Yes, I think you start to remember. So we mentioned this in previous classes before in electrical circuits. AC means alternating current, which means you have dual polarity, positive and negative. So as you can see here, you have part of the waveform positive, another part is negative. So you have both of polarities, dual polarity supply. So this is called AC or alternating current supply. In the second waveform here, the output volt, we have only positive supply. We don't have negative parts of the waveform. So this is DC supply. Someone can say DC supply is constant value. I will say, okay, but this is a pure DC supply. So the pure DC supply is constant value. But the waveform you can see here, this waveform here is DC supply. Why it's DC supply? Because it has single polarity. Okay, it has only positive here. If it has only negative also, so it will be a negative supply, negative DC supply. Here it's a positive DC supply. It's not constant, but it's still DC supply. Okay, so this concept has to be very clear. For that, guys, the output of this rectifier circuit now, just one diode, the output is considered as a DC output. DC output. It's not pure or ideal DC, but it's still a DC output. Okay. In this example here, consider the circuit shown in this figure here. Assume that VB equals 12 volts. So the supply volt, we have VB, which is the battery here, equals 12 volts. And we have a resistance of 100 ohms. This is our resistance here, is 100 ohm. And we have a diode, as you can see here. And also, this diode is given V gamma equals 0.6 volt. And we assume that the supply volt is 24 sine omega t. 24 sine omega t, so this means the peak value is 24. The RMS equals 24 divided root 2. Okay? So, this is our circuit. What do we need here, guys? We need to determine the peak diode current. So what is the peak diode current? Then what the maximum reverse diode, what the maximum reverse bias diode voltage, the maximum reverse voltage across this diode, and the fraction of the cycle over which the diode is conducting. What the meaning of the fraction of the cycle that or over which the diode is conducting? So you have a cycle of 360 degrees. How much or how long the diode was conducting here during this 360 degrees? Is it conducting for 180 degrees, less, 90, whatever? So we need to determine how long the diode will be conducting here in this circuit. Firstly, guys, I'd like to elaborate more discussion about this circuit here. Actually, this circuit can be considered as a battery charging circuit. So the battery charger is actually work with the same concept. What's the concept? This is our load, which is our battery. The charger has internal resistance and diode. That's it. We may have some other elements for protection, but this is the basic circuit of a charger. Okay. So we can consider also the adapters or chargers of computers or mobile phones. All of these also depend on the rectifier in the operation. Okay, so it has internal rectifier circuit in the device. So let's see together, guys, how can we solve this question. Firstly, the question is when this diode will be on. So let's review together what the condition for a diode to be turned on. So the condition is V anode minus V cathode should be greater than V gamma. So this is V anode, this is V cathode. So VA minus VC should be greater than V gamma. Now, what the value of the cathode volt even if the diode is open circuit? Right? So the value of this volt here, if this diode is open, it will be V battery. So the condition here to turn this diode is gonna be VA should be greater than V cathode, which is battery volt, plus V gamma. So this is the condition. And V anode is nothing but the volt at this terminal, which means V supply minus I times R. So if VA, which is Vs minus I times R, is greater than V gamma plus V battery, this diode will be turned on. So this is the condition now. This will happen at which time? We don't know. Let's assume this time is called omega T1. This angle is omega T1. The time is T1. Okay. And the amount of output volt here, sorry, this is the amount of current here. So this is I. Okay. And we don't know yet the value. We need to make the calculations now. And I will start when V supply is greater than means after this point in this direction, greater than V battery plus V gamma. Okay. So this is the condition now, guys. So this is the first point. The diode will be on and the diode will be off if the current reaches zero again at the same or the identical point here. So this is the curve, and we need to identify or determine the required parts here. We need the diode peak current. So what the peak value here we have. We need the maximum reverse voltage. So we need to draw the volt of the output and see what the maximum output volt we have in this circuit here. Okay, so this is slide, guys, it came here by mistake. So this is the beginning of our solution. So let's see, guys, the solution here. Firstly, I peak, we can say I peak equals V supply peak minus V battery minus V gamma divided R. So I didn't calculate the RMS values here. So I will take the V supply as a peak value. So Vs here, guys, is a peak value. And we mentioned that this peak value is 24 according to the relation we have. It was 24 sine omega t. So 24 is the peak value. So 24 minus V battery, which is given 12 volts, minus V gamma, which is given 0.6, divide R, which is our limiting resistor, 0.1 ohm. So this gives us 114 milliampere. So this is the peak value of our current. So this is the first thing needed here. The second part is what the maximum reverse bias diode volt. We mentioned, guys, let's go back to the circuit again. We mentioned, guys, that in half wave rectifier, the maximum volt is the same as the peak of the supply. But here, our load is not resistance. So what do we expect is it should be the peak value of the supply minus the volt at the cathode side. So in this case, it would be V maximum supply plus the 12 volts. So the peak value is 24, so it's gonna be 24 plus 12, which means it's going to be 36 volt here. So once we have a battery in our load, the maximum reverse volt will increase. Okay, so this is one of the drawbacks, by the way, of this circuit when we compare it to other rectifier circuits. So we have a problem here, which is the peak reverse voltage value of the diode here is relatively high. Okay. Now, regarding the diode conduction, we need to know the period that the diode was turned on. Let's go back again to the circuit. So we need to know what is this period. This period means we need omega T2 minus omega T1. So this is the conduction period, or let's say conduction angle. Okay. And if you'd like to get T, you can get it from 2 pi f. But actually here we don't have even the frequency of the supply, so it can be just a conducting angle here in this example. Okay. Okay. Because he didn't ask the conduction time. He just said the fraction of the cycle over which the diode is conducting. So we need to know what the fraction compared to the 360 degrees. Okay. So how can we get it, guys? So we can get it simply by, here, guys, the condition of omega T1 is current is going to be 0 at omega T1. And at omega T1, can you see here the supply volt equals V battery plus V gamma. So if you say now V battery plus V gamma is going to be equal to Vs at omega T1, so we can say Vs of omega T1 equals V battery plus V gamma. And V of omega T1 means 24 sine omega T1 equals VB, which is 12 volt, plus V gamma, which is 0.6 volt. So we have an equation here with one unknown, which is omega T1. So we can calculate omega T1 from this equation. So simply, we can say, guys, now V1 equals 24 sine omega T1 equals 12.6. So sine omega T1 can be calculated, and we can get omega T as sine inverse. 12.6 divided 24, you will get the value 31.7. Actually, if you have a look to the waveform again here, guys, this will happen twice. So Vs will be equal to Vb plus V gamma at two angles. But because of the symmetry of the sinusoidal waveform, if this angle is omega T1, so that the other angle here, this term also equals omega T1, which means this part of the waveform is nothing but 90 minus omega T1, which is omega T2. Okay, guys. So from here, guys, we can calculate the conduction period as omega T2 equals, it could be 180 minus omega T1. So this is omega T2, 148. So we have omega T2 and omega T1 now. If you subtract both of them and compare it with the 360 degrees, you will get the ratio. And if you need it in percent, so just multiply times 100. So we got that 32.4% of the waveform of the 360 degrees, the diode will be conducting. Okay, so this is the question regarding the portion that the diode will be conducting in this circuit. Here we have a comment. So this example shows that the diode conducts only approximately 1/3 of the time, which means the efficiency of this battery charger is quite low. Why? Because the conduction is very little time in the circuit. So we expect to have lower efficiency for these circuits. Okay. Full wave rectifier. So we discussed now the half wave rectifier. For the full wave rectifier, this is the concept of the full wave guide. So if you have a center tap transformer, what's the meaning of center tap transformer? Center tap transformer means you have one primary winding. This is the primary winding, and another secondary winding here has two halves. What the voltage shape for every half? So can you see the output volt here is in phase with the input volt here. So the diode D1 is going to conduct during these periods. Okay. What will happen in the second half? In the second half, actually, the volt will be reversed, so it will start from this instance here. And in this case, the volt will be reversed, which means the diode D2 will be conducting in the next half. And if the diode D2 is conducting in the next half, it's going to connect the positive to the top level again, or to the output resistance again, which means now all of the time the output is going to be positive. So this is the waveform now. So can you see here, guys? We have on the top here plus minus Vs, and we have here plus minus Vs. So what will happen is, if this is plus, this will be plus at the same time. If this is minus, this will be minus, which means this will be minus and this will be plus, so the diode D2 will be on. So during a positive half cycle, D1 will be on. During negative half cycle, D2 will be on. And whatever, during positive or negative, this point all of the time will see the positive cycle only, which means now we could convert both of half cycles to positive. So this is one advantage compared to the full wave rectifier. So to half wave rectifier. Now we can have both of half cycles on the output. Okay. Regarding the volt, so you will have a difference of V gamma as well, like the previous case also. Okay. And the relations, as you can see here, V secondary equals V1 times N2 divide N1, just applying the turns ratio of a transformer in order to see the output voltage magnitude. Okay. The turns ratio of the transformer, usually designed N1 times N2, can be designated to step down the input line volt to a value that will produce a particular DC output volt in the rectifier. So if you need, for instance, a peak value of 12 volts, so you should select your transformer to be, for instance, 110 to 12 in order to have this value. Okay, so the turn resistance should be designed based on this case. The input power transformer also provides electrical isolation between the power line circuit and the electronic circuit. This is very important point, guys. In most of applications, guys, you know, guys, any application, we have a standard for this application. So for electrical circuits, for electrical devices, we have a standard we are following. Okay. Most of the standards in applications require isolation for the loads. Let me give you an example, for instance, for electric vehicles. You know that electric vehicles should be charged. Can you imagine what will happen if you have a short circuit coming from the input side of the charger? So it will affect the circuit of the electrical car itself. So this is not allowed. So in order to avoid that, we have to use protection, and one of the protection schemes is using isolated transformer. So the isolation is very important. Okay, guys? So it's recommended to have isolation in our supply. This is one of the important things in our standards. Okay? So this is one important point, guys, you have to understand. So the isolation reduces the risk of electrical shocks for any application. During the negative half cycle, so as you can see here, guys, here this is a simulation for the negative half cycle here, and diode 2 will be on during that half cycle, and this is going to be the next part of the circuit. So we already discussed this in the previous slide. Okay, so this is just animation to see how the circuit is working in the positive and negative half cycle. As a conclusion, guys, we can make a characteristic now for our rectifier circuit. So compare this to the half wave rectifier. We could see in the half wave rectifier, we have only this part of the characteristic. But for our full wave rectifier, you have this part as well. Why? Because if V in the negative side is less than minus V gamma, you will have V out also in positive like that. So this is called the transfer characteristic of the full wave rectifier. Before moving to the second part, guys, we need to see one important thing here, which is what is the voltage drop across these diodes? If you have a look here, guys, all of the time, guys, we consider the voltage drop during open circuit. So if this diode is on, which means it's short circuit, so this diode is going to be open circuit. Or let's say the opposite, because this is conducting here in this shape. So let's say this is conducting and this is open. So this is open circuit now. Open circuit. Okay. Let me erase to avoid any confusion here. So this is open circuit and this is short circuit. So this is short circuit, meaning this is on and this is off. So this is open circuit. So if I'm going to draw this circuit outside, so the transformer secondary is here. This is the first part of the coil. This is the second part of the coil. Diode is on, so this is short circuit. We have here, this is our ground. Here is our load connected to ground, and the same point is connected to the other diode from the other side. So this is now the open circuit of D1. Here we have VS, and this is also VS. During turn on, this VS became here positive, and this is the negative, and the volt here is V peak is VS all of the time. So here you have VS, and here you have VS, but it will be reversed during this off. So if you calculate V anode minus V cathode, you will find that V D1 at turn off equals 2 VS, which means twice of the peak value of our supply. So the peak reverse volt here is relatively high. How can we reduce it? Simply, we can reduce the volt by sharing this volt with another device, which means connect another diode in series in order to distribute the volt between both. And this is actually the idea of the full bridge rectifier. So the idea of full bridge rectifier is to operate two diodes in series with the load and supply. So This is our supply here in the left-hand side in figure A. This is our secondary volt. If we have D1 and D2 on together, so this one will be on, the load, the current is moving through the load here and return back through D2. So we have two diodes connected in series. During this time, guys, you will find that D3 and D4 are open circuits. And if D3 and D4 are open circuits, so the voltage across D3 and D4 will be divided together. So by the end, you will find that the volt across this diode equals secondary voltage by 2. So the voltage drop across this diode is less in case of the full bridge configuration. And this is one of the important advantages of the full bridge configuration. The only drawback compared to the other circuit is the peak value is going to be reduced a bit. Why? Because you have two diodes connected in series, which means the conduction of the two diodes, you will have 2 V gamma during turn on. So V output peak value is going to be supply or secondary transformer voltage minus 2 V gamma. But the other one was Vs minus V gamma only. Okay. However, again, for high power circuit, this is relatively small volt and we don't care about it. So we do prefer to use the full bridge rectifier compared to the previous configuration, which is called center tap configuration. One more thing, guys, the center tap transformer is more expensive than this 2-winding transformer. So we do prefer, guys, to use this circuit configuration compared to the center tap one. Firstly, the diode is going to be less cost because you have less voltage diode. You will have less losses, by the way, and at the same time, the transformer price is less. Okay, so we do prefer to use the full bridge over the center tap transformer. Let's solve this example together, guys. In this example here, we need to compare the voltages and the transformer turns ratio in the two full wave rectifier circuits. So this is very interesting problem because it will show us the difference between the half wave and full wave rectifier. Consider the rectifier circuit shown in figure 2.5, the previous figure we had. 2.5a and 2.6a, which are the half wave and full wave. Assume the input volt is 120 volts. So we have 120 voltage source and 60 hertz AC supply. The desired peak output volt is 9 volts. So this is the DC output needed, 9 volts. And the diode cut-in volt is assumed to be 0.7. So V gamma, can you see, guys? He gave it another name here. Cut-in volt. Cut-in volt is the turn-on volt as well. Okay? So this is V gamma equals 0.7. So let's compare the circuits together now. Let's start with the center tap one. So for the center tap circuits, the peak volt is required to be 9 volts. So 9 volt is going to be V out plus V gamma. The transformer volt V secondary of the half of the center tap should be V out maximum, which is 9 volt plus V gamma. So 9 plus 0.7 is 9.7 volts. So this is, if this is a center tap transformer here, so this volt here should be 9.7. And you will have another 9.7 down here. So this is the transformer here. For a sinusoidal signal, this produces an RMS volt of, if this is peak value, so the RMS is going to be 9.7 divided root 2. So this is 6.86 volts. So 9.7 peak. And the RMS is 6.86. Any sinusoidal waveform, guys, you know that RMS equals maximum divided root 2. So this is the RMS volt required for the half or the center tap transformer of the secondary side. Now, The turns ratio of the primary should be now 120 over the 6.86. So 120 over 6.86, it gives you around 17.5 turns ratio. So this is the turns ratio of our transformer in case of center tap. What about the bridge configuration? So for the bridge configuration, V out maximum plus 2 V gamma is the secondary volt. So you have now 2 V gamma, 2 times 0.7 plus 9, so 10.4 volts. The RMS value of this value can be obtained by dividing over root 2. So the secondary RMS value is going to be 7.35. So the turns ratio now of this transformer is going to be 120 divided 7.35, which is 16.3. So this is the turns ratio in case of the full or two-winding transformer. But the previous one was the center tap transformer. So we compare now regarding the transformer types. Regarding the peak reverse volt. Now the peak reverse volt for the center tap, as we mentioned, guys, is going to be 2V maximum minus V gamma. So 2 times 9.7 volt, this is the maximum volt, minus 0.7, so this is the maximum volt across diode. So this is the peak reverse volt for the diode in the center tap configuration. For the other configuration, the peak reverse volt is going to be VR maximum equals VS maximum minus V gamma, so 10.4 minus 0.7, which is 9.7 only. So this is the peak reverse volt. Can you see, guys? The diode in the center tab almost need twice of the voltage magnitude of the diode in the bridge configuration. So these are the comments we have here. These conclusions demonstrate the advantage of the bridge rectifier over the center tap transformer circuit. First, only half as many turns as are required for the secondary winding in the bridge center rectifier, because the voltage magnitude, as you could see. This is true because only half of the secondary winding of the center tap transformer is utilized at any one time. For that, the center tap transformer is relatively high price. The second thing is the bridge circuit, the peak inverse voltage that any diode must sustain without breakdown is only half that of the center tap. So we can conclude these guys in 4 points, as you can see here. The drawback of the center tap circuit: high peak inverse volt, heavy weight and larger size because of transformer, because of the center tap transformer. High magnetic losses. Why high magnetic losses? Because the center tap transformer is relatively higher in size, and bigger size will have higher losses. So the efficiency is expected to be lower, and at the same time expensive due to the transformer center tap as well. So you have 4 points drawbacks in the center tap circuit compared to that of the full bridge rectifier. Here, this note is nice because sometimes people say in the center tap transformer we can have dual polarity power supply. We can have positive and negative power supply. The same also, you can obtain the same from the full bridge rectifier. How? Just by reversing. So we can produce negative rectification by reversing the direction of diodes in either circuit. So you can get positive or negative because this is something depend on the reference you will select. Okay, guys. If you remember, in the first slide, we discussed something related to filter. in order to have pure DC supply. So we need to understand the concept of filter together. I will give a hint about the filter, and we can continue discussing this in our next class because this point needs longer time. Let's firstly see what will happen if we have a capacitor here in our circuit. So this is our AC source now. This is our AC source. We have our diode, and this is our load. But instead of just supplying, I added a capacitor here. What this capacitor is going to do in this circuit? If we assume that the diode is forward, so sorry, if we assume the forward resistance of the diode is 0, so assume that it's ideal diode, which means that the RFC time constant is 0. RFC means the RF of the diode and the capacitor together will have a time constant equal to 0. So this means the voltage across the capacitor follows the initial portion of the signal voltage, which means the capacitor will be charging with the exact value of your supply. So as you can see, this is going to be the capacitor volt here. Okay. For sure, it should be less with the value of V gamma. Then what will happen? This will be valid until reaching to the peak value here. Then let's see what happens if the diode is turned off. When the signal volt reaches its peak value, so when it reaches to the peak value here, so it will start decreasing. And when the supply volt here is decreasing, this capacitor is charged. Okay, so the voltage across the capacitor also starts to decrease, which means the capacitor starts to discharge. So the capacitor will start discharging from that point. But the diode, we used to have the diode turned off in the half-wave rectifier at this instant. But this will not happen now because you still have a supply and the capacitor is going to supply our load because the capacitor will discharge in this resistance. So once the voltage here starts decreasing and reach to the capacitor volt, this diode will be turned off. And the load current will continue operating, depends on the current coming from the capacitance. So what will happen is the capacitor will continue discharging in the load by means of the time constant of the load resistance and the capacitor value. Until which time, guys? Until the diode, sorry, the capacitor volt reach to a certain limit, so the capacitor volt is still discharging here, until the supply volt became higher than this capacitor. So what will happen? The diode will be turned on again. So in this case, guys, the diode is turning on from this instant to that instant, and again from this instant to that instant, and so on. And in this case, the output volt never reaches 0. So this is the concept now. So once we added a capacitor in our circuit, coupling capacitor or smoothing capacitor, the ripple voltages will be less. Instead of having ripples, it was from the peak value to 0. Now the minimum value will be this value here. So the ripples will be less if we added a capacitor here. What's the relation of this output volt, guys? So V out equals V maximum, which is the peak value of the AC supply, times E to power T prime divide tau, where tau is the time constant of the capacitor and load resistance. So this is, guys, the equation that describes the output volt in these circuits. Okay. Okay. So how can we get the ripple volt now? The ripple volt is nothing but the peak value minus the minimum value. So the peak value is V maximum. The minimum value is the point here where the capacitor volt will equal to the supply volt. He call it here VL, and he made a relation here. Okay, so we don't need the exact. You can follow the revision, guys, in order to see the steps just to give the relation, but you don't need to memorize this in our course, so it's not that important. We just care about knowing the result here. So the ripple is gonna be, by the end, V ripple equals V maximum divide 2F divide RC. Now this need to be discussed. So the ripple volt depends on some important factors. What are these factors? V maximum is the supply volt for sure. So let's exclude V maximum because this is the supply volt and it's not a controlling parameter. Frequency, this is the supply frequency. It's not a controlling parameter as well. Resistance, the load resistance is not a controlling parameter because if you supply a certain load, you will be forced to use a certain resistance. So you will find that we can say here V ripple is proportional to 1 divide C. So it's inversely proportional to the capacitance magnitude. So the higher the capacitance value, the lower the ripple voltage in a rectifier. Okay, guys, so this is very important. So how to reduce the voltage ripples in a rectifier? We just need to increase this capacitor. Okay. Next class, we will elaborate more and start solving this example because the time now is very short. Thank you, guys, and have a nice weekend. Just last thing, the homework will be available on eCampus by the during this weekend. Okay, and just I would like to remind you, we will start our lab in the coming Monday at 5 p.m. It will be synchronous. I will share with you on eCampus the link of our class. So please be on time at 5. It's not important to be in the lab for the next session. Next session, you can make it from your home or whatever. It's up to you. But what's important, you need to have your computer and you will install the Spice in order to use it on your computer during our semester. Thank you so much, guys, and have a nice weekend.